Hey guys, welcome back to my channel. It's me Vijay. The Nobel Prize is the most coveted prize in sciences. Scientists and researchers around the world wait for their chance to redeem this most coveted prize. And many scientists spend their whole lives dedicated to researching and to the field in which they get the Nobel Prize in. And this year, the Nobel Prize in Physics was given to a group of three people who have spent a lot of time researching on their topic, that is quantum tunneling. But quantum tunneling has various applications in various fields. It's not just in science or technology, it's there in various biological activities that we do and also many technical activities that we do. So their research is also exploring quantum tunneling, this phenomenon, and a specific function that quantum tunneling does in which is related to cell phones and cell phone technology. And coincidentally, I've also been doing an investigatory project on quantum tunneling. So I wanted to give my understanding of what I've understood from quantum tunneling and what it's about, and a brief understanding of what these scientists have accomplished and how much effort that they've put into this achievement. So let me try to give you my understanding of what quantum tunneling is. So every day we encounter systems that are completely classical. Systems are our surroundings, including us and the objects around us. Now, a classical system means that these objects around us and us ourselves obey the laws of motion given by Newton. If the objects are very, very minute, very, very small, like an electron or a really tiny particle, these particles or electrons may not follow the same laws of motion as other objects, other huge objects. And this is given by Heisenberg's uncertainty principle, which is a scientific principle that helps us understand how really small particles behave differently than normal objects that we see around us. In this minute scale of electrons and tiny particles, the quantum mechanical laws are followed. And quantum tunneling is also a quantum mechanical process. So we can understand quantum tunneling through a really simple analogy. Imagine that you have to cross a mountain from one side to another. You would probably have to walk up the mountain, climb the mountain, and then climb down again. That would require a lot of energy. You would have to spend a lot of energy in climbing the mountain and again going down the mountain. But if you were, say, a really tiny particle or an electron, you could go through quantum tunneling and pass through the mountain itself without actually having to spend as much energy in climbing and climbing down again. You could just pass through the mountain without having to climb it. And this is basically what quantum tunneling is. It's basically that the electron is in an orbital which is not a determined path. It is a 3D path where the electron has the highest probability of being in. Now, in quantum mechanics, sometimes the probability of passing through the barrier that has higher energy than the particle itself, sometimes the electron can pass through the barrier. And this is basically the principle on which quantum tunneling acts on. Now, quantum tunneling has many applications, real and everyday applications, and such as microscopes to see elements like gold or graphite and to understand how the particles look like. It has many more applications, and the scientists who won the Nobel Prize in Physics have also researched upon a topic in quantum tunneling which has real day impacts. Who won the Nobel Prize for Physics are John Clarke at the University of California, Berkeley, Michel Devoret at Yale University in New Haven, Connecticut, and Santa Barbara. The reason that they have won the Nobel Prize is because of their research on the implications of quantum tunneling on electronics. And a major question in physics is how big can the size of a system be that still demonstrates quantum mechanical effects? And the team that won the Nobel Prize conducted experiments with electrical circuits in which they demonstrated both quantum mechanical tunneling and quantized energy levels in a system big enough to be held in the hand. So it doesn't have to be minute, it doesn't have to be really, really small. It can also be big enough to be held in the hand. In 1984-1985, John Clarke, Michel and Michel and John M conducted a series of experiments with electronic circuits built of superconductor components that conduct a current with no electrical resistance. In the circuit, the superconducting components were separated by a thin layer of non-conductive metal, and this is known as Josephson's junction, and it's used in electronics and in circuits. And by refining and measuring all the various properties of their circuit, they were able to control and explore the phenomena that arose when they passed a current through it. They charged particles moving through the superconductor, which was comprising of a system that behaved as if they were a single particle that filled the entire circuit. I hope that this helped you understand what they have done, and science is really interesting and it has many applications in the real world, and that's all this video is about.